Hello, my name is Tobias Duerig. I'm a volcanologist at University of Iceland. In this video, we will review the basic physical principles that control the formation and evolution of volcanic plumes. In explosive eruptions, the magma is fragmented into a mixture of tephra and volcanic gases. These mixtures form what we call volcanic plumes. The term tephra is used for all solid material thrown into the air by a volcanic eruption. The larger material, blocks and bombs, do not travel very far and are usually found near the crater. But convective plumes can inject significant amounts of fine fragments, known as volcanic ash, high up into the atmosphere. The fine ash is often carried by the volcanic cloud for tens or even hundreds of kilometers. The fallout from volcanic plumes can cover roofs and vegetation and can be a threat to people and animals. High concentrations of ash in the atmosphere can pose a serious hazard for air traffic. During explosive eruptions, volcano observatories and ash advisory centers need to monitor the plume evolution and make every effort to forecast the hazards in a timely manner. Volcanic plumes are composed of hot pyroclasts, that is, juvenile fragments, crystals and lithics, hot magmatic gases, and entrained air. In phreatomagmatic eruptions, also significant amounts of water can be present. Volcanic plumes are therefore turbulent multi-phase flows featuring complex heat transfer dynamics and a continuously changing bulk density. Knowing the general physical processes is essential for understanding a plume's behavior. First, let's have a quick look into the density of the Earth's stratified atmosphere. The further you go from the Earth's center, the more the atmospheric density decreases due to the decreasing gravity. This trend is indicated by the blue dashed line. How does the bulk density of a plume look in comparison? We can identify three main regions. Right after exiting the conduit, the turbulently ejected mixture is controlled by the momentum it got from the kinetic energy released by the explosive fragmentation processes and expanding gases. The lower region is the so-called gas thrust region, and the momentum-driven mixtures are also known as jets. In the gas thrust region, the vertical velocity of a jet rapidly decreases while cold air is entrained and heated up. This causes the jet to increase in volume while its bulk density is reduced. When the bulk density of the jet is below the density of the atmosphere, another mechanism takes over, which we refer to as buoyant convectivity. Like a gas balloon that is lighter than air, the ash column ascends now driven fully by buoyancy. The zone in which this happens is called the convective region. There, the plume is characterized by large eddies, which entrain significant amounts of cold air into the column. The entrained air is heated up, expanding the column radially and fanning the convective currents that further increase the lifting forces of the plume. In the convective region, the vertical velocity is relatively constant, or can even increase. This phenomenon is also known as superbuoyancy. At a certain height, the bulk density curve of the hot rising plume intersects again with that of the cold, thin atmosphere. The transported particles and gases now spread laterally in the region called umbrella region. The umbrella region is the most characteristic feature of any volcanic plume and can extend downwind up to several hundred kilometers. Since the rising convective mixture has some remaining momentum, a part of the column can overshoot the level of equal density. As a consequence, it evolves into a gravitational flow which spreads ash evenly, also in the upwind sector of the umbrella region. The transition between gas thrust and convective region is crucial for the behavior of the flow and how the plume evolves. Jets, which do not entrain enough air to experience a sufficient reduction of their bulk density, will not become buoyant. Instead of forming a convective plume, the column collapses, forming surges, also known as pyroclastic density currents or PDCs. These surges reach high velocities and can be very destructive. The hot mixture of tephra and gas is in most cases deadly to people and animals. The coarser particles are sedimented during the process, which leaves a mixture of finer grains with reduced density that can become buoyant. The result is secondary convective plumes called Koignen-Bright plumes. They lack a gas thrust region and are characterized by the shape of an hourglass. What controls the evolution of a volcanic plume? What's important are the conditions at the source summarized as eruption source parameters. These include the total grain size distribution, the exit velocity and bulk temperature of the mixture, and the diameter of the conduit. A key eruption source parameter is the mass eruption rate, or MER, which quantifies the mass of volcanic material ejected per time and is given in kilograms per second. Depending on the eruption intensity, mass eruption rates can range from some thousands to more than 1 billion kilograms per second. Unfortunately, the mass eruption rate cannot be directly measured in real time. A typical indirect approach is to measure the plume height and apply plume models. Those provide a mathematical description of how the height of the plume and the mass eruption rate are related, generally in form of a power law. Eruption source parameters are not the only factors that control plume behavior. Other influential parameters are, for example, the humidity of the atmosphere, particle segregation and re-entrainment, and, most importantly, the processes that control the entrainment of air. Especially weak plumes from eruptions with relatively low mass eruption rates can get significantly wind affected. A strong wind field causes the plume to shear, taking on a characteristic bent-over shape. The wind-enhanced additional entrainment of cold air causes an earlier dilution of the plume. Both effects can cause a significant reduction of plume height compared to plumes in a windless environment. Let's summarize. Volcanic plumes are turbulent multiphase mixtures composed of tephra, magmatic and atmospheric gases, and water. A plume is characterized by 3 zones: the gas thrust region, where the plume is fed by momentum-driven jets, the convective region, where the only lifting mechanism is convective buoyancy, and the umbrella region, where the ash spreads laterally in an atmospheric layer of equal density. If the transition from jet to buoyant plume fails, the column collapses, causing pyroclastic flows that are rushing down the flanks of the volcano at high speeds. These PDCs are highly destructive and can again be the source of buoyant ash columns called Koignen-Bright plumes. Plumes are controlled by eruption source parameters and atmospheric conditions. Especially for weaker plumes, wind speed is an important factor. A key measure of the eruption intensity is the mass eruption rate, MER, which quantifies the amount of volcanic material ejected per time. It is impossible to be directly measured in real time. A typical strategy is therefore to apply plume models, using the height of the plume as a key input parameter. More information on volcanic plumes can be found in the following books.